Before we start this video, there's a lot of information covered here, so feel free to skip around, and I've left bookmarks in the video description so you can actually browse around for parts that you may have trouble with. So a set is basically a collection of things or objects. You can have anything inside your set, so you can have a set of UK cities or the set of shapes. For example, circles, triangles, squares. Here I've got two sets. So A here is the set containing a cat, a dog, and a rabbit. B is the set containing the numbers 1, 2, and 4. Notice here that the sets we denote as capital letters. So compared to lowercase letters, where we normally reserve that for variables, such as here a equals 2 in lowercase, sets we use uppercase letters. In sets, the order of the elements in a set do not matter. So look at these three sets over here. All of them contain the numbers 1, 2, and 4, but in different orders. So here it doesn't matter. All of these three sets are equivalent to each other. So normally when we write sets, we start off with the lowest number first and the highest number at the end, so in ascending order. Compare this with tuples, for example, where the order of numbers does matter. So for example, the coordinate here, 1, 2, 4, is not the same as the coordinate 2, 4, 1. So you can see that the x coordinate over here is 1 and the x coordinate over here is 2. So these two coordinates are not the same. Also, we disregard duplicate elements within sets. So these two sets would be the same even though on the left hand set we have 3 2's. So here we can ignore these additional 2's over here. Some more notation. So this symbol over here means belongs to, whereas this symbol over here means does not belong to. So anytime you see these symbols, you can just replace it with the corresponding words. So for example, 4 belongs to this set. So 4 is a member of the set. Whereas 10 does not belong to the set. So 10 is not a member of this set. Now let's look at ways where we can combine two sets together. So this symbol over here you're probably familiar with. This symbol means union. So like the name implies, if you take all the elements in A and all of the elements in B and combine them into one larger set, then you have the union of those two sets. Similarly over here, this symbol means intersection. So unlike before where we're looking at combining all the elements together, here we're just looking for all the numbers that appear in both A and in B. So in this case only 4 appears in both A and B, so the intersection of these two sets is 4. Another way of writing this is as follows. So we're looking for elements that are both in A and also in B. So this is just another way of writing this set. Compare this to before when we're looking at the union of the sets. So x can either be in A or x can be in B. Finally, we have this slash here, which means difference. So this altogether means A slash B, or the difference of A and B. And how to work it out is if we start off with the elements in A, so we have the elements 1, 2, and 4, and we remove any elements that are also in B, which in this case we remove 4 because 4 is also in B. So what you end up with is just the numbers 1 and 2. Similarly, we can do it with the elements in B. So here we have the numbers 3, 4, and 5, and we remove any elements that are also in A. And since 4 is in A as well, we removed 4, and what we have left is 3 and 5. Similar to what we had done before, we can rewrite A/B as the following. So in order to be in A/B, then X has to be in A and X must not be in B. So let's go over it a different way. So imagine we have a Venn diagram where we can represent A and B as two circles on a Venn diagram. So let's say that A, as before, contains 1, 2, and 4, and B contains 3, 4, and 5. So how do we go about labeling this Venn diagram? Well, it's simple here. Since 4 is in both A and B, we can put it in the middle, and then we can put the numbers 1 and 2 here, and the numbers 3 and 5 over here. Let's mark this area in blue over here. So this area in blue is A union B. The area where these two circles intersect, as drawn in green over here, we can say that it's the intersection, so A intersection B. This area over here, as marked by pink, is where all the elements are in A, but they're not in B. So we can mark it as A/B. And then this area over here are elements which are in B, but not in A. So we end up with B/A. So hopefully this image you can use just to clarify what the symbols mean. So let's look at more than two sets over here. So this maybe seem unfamiliar to you, but think of it as similar to a series notation or sigma notation. So what this means is we're taking the union of an from n to 1. So essentially we can rewrite this as the following: A1 union A2 union A3. So here, this just basically represents multiple usage of the union operator on 3 sets. And in this case, it's just the numbers from 1 to 7. Similarly, we can use the intersection operator here as well. So we can write this as A1 intersection A2 intersection A3. So the intersection of an from n equals 1 to 3. So the intersection of an from n equals 1 to 3 is just A1. So the intersection of an from n equals 1 to 3 is just basically the A1 intersection A2. So here, this just basically means the intersection of an from n equals 1 to 3, and this just basically means A1 intersection A2 intersection A3. Since 4 is the only number that appears in all 3 sets, then we say that this intersection here equals to 4. Moving on, so this symbol over here means subset. So what is a subset exactly? Well, let's just label these two sets over here, A and B. So in essence, A is a subset of B if all the elements in A appear in B. So we can actually check this for ourselves in this example. So let's see, we start off with the first element in A, that's 1. Yep, there's a 1 in B. And then there's a 2 in A, and we can check that there's also a 2 in B. And likewise, there's a 4 here, and there's a 4 here. So we have just confirmed that every element in A appears in B, so A is a subset of B. However, this example, we can see that A is not a subset of B, because although we have a 4 here, we don't have a 7 in B. So we can say that A is not a subset of B because not all of the elements of A can be found in B. This symbol over here means superset, but in essence you can just think of this as the reverse of a subset. So if I were to rewrite this out so that we switch the places around of the two sets, then in essence we can say that the set on the left hand side is a subset of the set of the right hand side. So we just basically switched the two sets around, and so that these two statements over here are equivalent. A quick exercise just to check your understanding is to verify the following. So imagine we have two sets A and B such that A is a subset of B and B is a subset of A. So you can verify this for yourself, that this is the same as saying that A equals B, i.e. A and B are the same set. A point related to the example before is that a set can be a subset of itself. So we can see that both sets here are equal to each other because they contain the same elements. But let's actually verify that they are a subset. So let's have a look over here. So if we take 1, well, 1 appears in this set on the right, so does 2, and so does 4. So in actual fact, A is a subset of A. If I wanted to be more precise and say that one set is a subset of another set but are not equal to each other, then we can use this symbol over here. So if I say that A and say that's B, then we can use this symbol over here to mean a proper subset. So a proper subset fulfills these two conditions, so that A is a subset of B, but then A is not equal to B. So we use this symbol here to mean proper subset and fulfills these two conditions below. A few more points on notation. So this bars over here means cardinality, and what cardinality means is the size of a set, i.e. how many elements are in the set. So here, since there are 3 elements or 3 numbers in this set, we say that the cardinality of A equals to 3. If we're looking for a set that has a cardinality of 0, then we can find it in the empty set. So this means the empty set. So this 0 with a slash through it means empty set. And what it essentially is just a set that has no elements in it. So think of it like if a set was a box or a container, then you add numbers or elements into that box. Well, think of an empty set as just basically being an empty container. So there's nothing in the box, so it's an empty set. Some examples of sets that have infinite cardinality are as follows. So here we've got this Z with a double slash through it here, meaning the set of integers. So essentially numbers that are whole, so whole numbers. So you -3, -2, -1, 0, 1, and 2, all up to positive and negative infinity. This set over here is the set of natural numbers. So the set of natural numbers are what we think of as counting numbers or positive integers. So 1, 2, 3, 4, and 5 going up into positive infinity. Some mathematicians choose to include 0 in the set of natural numbers, but here, as well as the rest of this course, we're not going to include a 0 in the set of natural numbers. So the reason why mathematicians do this is particularly in the fields of logic and set theory, and you can investigate the reasons if you choose those courses later on. But if we want a set of non-negative numbers, so 0, 1, 2, 3, etc., then what we can do is just have n union the set containing 0 to represent 0, 1, 2, 3, etc. So Q over here is another set with infinite cardinality, and this is the set of rational numbers, what you can think of as the set of fractions. So the way that this set is written looks a bit funny, but essentially you can just write this as follows. So it's the set of numbers of the form a divided by b. So what we need to add here is what a and b are. So we use I use a colon here in this notation. They use as a bar, and what this means is such that. So you can replace it with the words such that. And so a and b are integers, and b, or the denominator in this case, is not equal to 0, otherwise we'll be dividing by 0. So we can read this set to be a divided by b such that a and b are integers, b is not equal to 0. And this represents the set of fractions or the set of rational numbers. So here 2/3 would be in this set, as 2 and 3 are integers, whereas pi cannot be written in this form. So therefore pi is an irrational number and therefore not in this set. Finally, we have r over here, which is the set of real numbers. So this is just basically any numbers that you can find on the real numbered line. So we have 0 here, we got pi here, we got -1/2 over here. And some examples, so the square root of -2 belongs in the set of real numbers, but I equal to the square root of -1 does not belong in the set of real numbers. One final thing is that we have this chain of subsets. So all of the natural numbers are in the set of integers, all of the integers are in the set of rational numbers, all of the rational numbers are in the set of real numbers. In fact, you can also write this as follows. So n is a proper subset of Z, which is a proper subset of Q, which is a proper subset of R. Some final examples over here. So when we looked at the set of rational numbers, or Q, we had a sort of a weird sort of a way of constructing that set. Here is another example. So here we've got this condition over here. So numbers that are in the form of 2n minus 1, such that n is a natural number. So let's actually construct this set. So let's start off with n equals 1. So n equals 1, we have 2 times 1 minus 1. So the first element of the set will be 1. And then if we take n to be 2, so 2 times 2 minus 1 is 3. And then if you continue along with this pattern, then you end up constructing the set of odd numbers. So this is just another way of constructing sets. As long as you have a condition here, and then you can generate any set that you like. So a final example to leave you with, have a think about this before I tell you the answer. So pause this video, but here, is this set over here equal to this set over here? Now, you might think that, okay, so we've got 3 over here and then 3 over here, so we can cancel out the 3's. But this is not the case. Remember back to what I said earlier, that a set can also be a container. So if I draw this out to be set A, and then let's fill this up with elements. So we've got 2 in here, we've got 3 in here, and we've got another set here, and we've got a 3 in here as well. And you might think, okay, we've got 2 3's over here, we can cancel each other out. But this is not the case, because these are 2 different objects. So in actual fact, 3 is not the same as the set containing the number 3. These are 2 different things. One of them is a number, the other is a set. So we can't cancel it out. Similarly, if we add in the empty set here, as there's no other empty set as a duplicate, we can't cancel that either. So in actual fact, what we end up with is this set over here. So we can say that A is not equal to B because it does not have this set 3 over here, and this empty set over here. Hope this video is informative. I'll see you again next time.